Hello all, a very good day to all of you. In this session, we will discuss all the questions that have come from analog circuits in 2016 set 2 gate examination for electronics and telecommunication branch. Okay. So you can see there are a lot of questions, right, that have been asked in this year. So 6 are of 1 mark and 5 are of 2 marks. So in total, 16 marks have been asked from this subject in 2016 set 2, right? So let us discuss all the question one by one. The first question is, the Ebers-Moll model of a BJT is valid for which modes of operation? Like active, saturation or cutoff, which mode it is valid? So in order to appreciate the answer, let us start building briefly the Ebers-Moll model of a BJT. So if you take the schematic of a BJT, right? Let us take NPN BJT. So it have 3 terminals, right? One is collector, another is base, another is emitter, right? So it is a NPN transistor. So I have the construction is like this, right? The emitter is having N-type semiconductor, the base is P-type, and the collector is again N-type. Okay, so this is my emitter, this is my base, this is my collector. So you see they are the terminals, right? The emitter current is coming out of this emitter, right? This is my base current and this is my collector current, right? If you see between emitter and base there is a PN junction. Again between base and collector there is another PN junction. Okay, so according to Ebers-Moll model, right, at the input I have a diode, right, whose cathode is connected to emitter and anode is connected to base. Right. Similarly, between base and this is my emitter, right? This is my base. Okay. Between base and collector also I have a diode like this. Mind you, the BJT is not a back-to-back connected diode. It has something more, right? So which is explained by this model, right? What it says, right? Whenever you forward bias the emitter to base junction, right, the current will flow through like this. Let the current be denoted by the IF, right? So if the BJT would have been a simply back-to-back connected diode, there would not have been any effect of the current IF in the base to collector junction. But in BJT, some part of my IF will be flowing through my base to collector junction. So I can denote it by a current dependent. I can denote it as a dependent source, right? Dependent current source, right? So this current is alpha F into IF. Okay. So what it says, some part of my input PN junction diode is flowing through the base to collector junction, or I can say base to collector diode, right? So this is the phenomenon of a transistor, right? It is not simply a back-to-back connected diode, because if it would have been a back-to-back connected diode, the input current in the base emitter junction would not have been affecting the current in the base to collector junction. Okay. Similarly, when there is a current in the base to collector junction, let us denote it as IR, right? Some part of this current will also flow through my emitter base junction or emitter base junction diode, right? So some part of the current, right, will be flowing through alpha R into IR. Okay, so let me repeat again. Whenever there is a current, because of the forward bias of the emitter, forward bias or reverse bias, that doesn't matter to me. Whenever there is a current in the emitter base junction diode, right, IF flowing from anode to cathode, some part of the current will be again flowing through the base to collector junction, which is denoted by alpha F into IF. It is a current source, which is dependent current source, right? Because this IF is depending on my emitter to base voltage. Okay, it's independent of my base to collector voltage. to the first order, right? Similarly, the alpha and IR is depending upon my in base to collector junction current IR. Okay. Also, I can say other word, it is depending upon my base to collector junction voltage. Okay, to the first order, right? So this is my reverse mode model. Okay, and this model is applicable to all the modes of operation. How it will be applicable? Let us discuss. Okay, so if you try to understand this one, right? Let us take suppose this is my VBC, this is my VBE. Okay, let us assume that if VB is greater than 0, my input base junction will be base emitter junction will be. So if VB, okay, so to the first order, what I am assuming, to forward bias the base emitter junction, I need the voltage of base emitter to be greater than 0. Similarly, to forward bias the base collector junction, I need the voltage to be VBC should be greater than 0. I'm just assuming that. Okay, so actually it should be around 0.6 to 0.7 volt, but for the sake of understanding, I'm assuming that if it is greater than 0, it is forward bias. So you see, what is the active mode of operation? For active mode operation, so first thing is active. We will take base to emitter junction, base to collector junction, right? So one is active. So for active, base to emitter junction should be forward bias. The same place VBE should be greater than 0, right? And VBC should be less than 0. Okay, because it should be reverse bias. So VBE should be greater than 0, VBC should be less than 0. So I am in this region. So in this region, I am having active modes of operation, right? And second is saturation. For saturation, the base to emitter junction should be forward bias, should be greater than 0, and base to collector junction also should be forward bias, should be greater than 0. So base to collector is forward bias, base to emitter is forward bias. So both are greater than 0. So I am in saturation region, in this region, saturation, right? And then both are reverse bias, right? Both are reverse bias. 3, I will get cutoff. Both are less than 0. So in this region, I have cutoff mode of operation. The one what is remaining is the base emitter is reverse bias less than 0, and base collector is forward bias is greater than 0. Okay, this is called inverse active. Inverse active. Okay, active. So this is called inverse active. Okay, so how this model is useful for all the modes of operation? Let me explain you with 1-2 example. First example, we say, let's take example of first one. Suppose it is active region. Suppose it is active region. Let me take another color, right? So when it is in active region, right? My base to emitter junction is forward bias, right? My base to emitter junction is forward bias, and so my IF will be greater than 0, and my base to collector junction will be reverse bias. So IR will be almost 0 or negligible. So IR will be almost 0, it's a reverse bias. Since IR is almost 0, alpha into IR is some function of IR, also almost 0. Okay, so when we are in active region, okay, alpha F will be there, and some part of my IF will be going to my alpha F into RF, nothing but my collector. Okay, so if I want to draw the equivalent model, right, in active region, so what I have is at the input I have a PN junction, the current flowing is IF, right, and at the output, since it is a reverse bias, right, I am making it a open circuit, just approximately an open circuit. Alpha F into IF. Okay, this is my collector current. Okay, this is my emitter current, this is my base current, right? So this model, when I want to apply to active mode of operation, will be looking like this one. Okay, suppose I want to take one more example. Okay, suppose I want to make this model for saturation region. For saturation region, right, both are forward bias, right? Okay, so since both are forward bias, right, IR will be there, IF will be there, right? So the input emitter current will be IE will be IF, right? This emitter current IF minus alpha R into IR, right? Similarly, my collector current will be, this is my IC, right? IC will be equal to alpha F into IF minus IR. So thing is, I can apply this model to any modes of operation. Whenever it is forward bias, I have to put that current here and here. Whenever, so let me repeat, whenever my base to emitter junction will be forward bias, then this and this will be there. Whenever my base to collector junction will be forward bias, then this and this will be there. So I can get current in any mode of operation, right? When it is cut off, this will not be there, this will not be there. So the current will be zero, so there will be no current, right? So the EBUS small model is applicable to all the mode of operation, right? Depending upon which diode is forward bias, I have to take that current, okay, and calculate that total emitter current and total collector current, okay. So the answer should be in all the mode, right? Option D, okay. So let's go to the next question. Okay, a long channel NMOS transistor, okay, is biased in linear region with VDS of 50 millivolt, okay, and is used as a resistance, right? Which one of the following statement is not correct? So when a long channel transistor, right, NMOS transistor, right, this is NMOS, right, when it operates in a linear region, what is the resistance offered by the drain, right? So when we are in linear mode of operation, right, linear region, the current ID, okay, in my transistor will be equal to mu1 Cox double by L into VGS minus VTH into VDS, okay, VDS minus VDS square by 2, okay. Since VDS is very small, I am neglecting this term, right? So this is equal to mu1 Cox double by L VGS minus VTH into VDS, okay. So what is the resistance offered? So for that, you have to take a derivative of the diode current divided by VDS, right? If you take the derivative of diode current with respect to the diode, sorry, if you take derivative of the drain current with respect to drain to source voltage, I will get 1 by the resistance offered by the drain to source, right? Because dID by dVDS is 1 by resistance, right? So if I take derivative of the diode, sorry, drain current, I will get the 1 by drain to source resistance. So equal to mu1 Cox double by L into VGS minus VTH, okay, because derivative of VDS will be 1, okay. So RDS will be equal to 1 by mu1 Cox double by L into VGS minus VTH, right? So you see what it is asking. If width is increased, the resistance is decreasing, right? If width increases, R decreases, right? That's right. If threshold voltage is reduced, if it is reduced, right, VGS minus VT will be reduced, so RDS will be increasing, RDS decreases. It is not right, right? Not correct, because if VT decreases, this term will decrease, so RD will increase, right? If length is increased, resistance increases, right? Because length will go up. If L increases, R increases, right? If VGS increases, the resistance is decreases, resistance is increases, right? If VGS is increased, right, what will happen to my RDS? RDS will be decreasing, right? So option D also is not right. Option C is right, right? So if threshold voltage is reduced, the resistance is decreasing, right? It is increasing right now, because if VTS is decreasing, my resistance is increasing. Similarly, if VGS is increased, the resistance is decreasing, right? So B and D both are not correct, right? Because if I increase VGS, right, my RDS will decrease, but it is given increase. It's not right. Similarly, if my threshold voltage is reduced, then VGS minus VTS will be reducing, so RDS will be increasing, right? So it is given is decreasing. So option B and D are not right, not correct. Okay. Let's go to the next question. Assuming that a diode in the figure has a on voltage of 0.7 volt, but otherwise it is ideal, right? What is the meaning of that is, if I want to on the diode, right, I need V anode minus V cathode should be minimum 0.7 volt, right? This is anode, this is cathode. So if V anode minus V cathode is greater than 0.7 volt, okay, it will on, right? So let us check that if it is on or off, then you can calculate the I2, okay? Because if diode is on, the I2 will be different. If diode is off, my I2 will be different, okay? So first check whether the diode is on or off, okay? So first let's assume that if we take some assumption, okay, assume diode is off. If diode is off, right, what is the voltage across R1? V R1 equal to nothing but V anode minus V cathode, okay, is equal to 2 volt into 2K divided by 2K plus 6K equal to how much? 4 by 8 equal to 0.5 volt. Since V anode minus V cathode is nothing but V R1, when I assume it is open, is 0.5 volt, right? So the diode definitely is not on. The assumption of diode is not on is right, okay? So the diode is off, okay? If diode is off, let me build the equivalent circuit. Okay, this is 2K, this is 6K, this is I2, right? So what is my current? I2, very straightforward. I2 is equal to 2 volt by 2K plus 6K equal to 2 by 8K is equal to how much? 0.25 milliampere. Right? 2 by 8K is 0.8. That's right. So the answer should be in milliampere means 0.25. Okay, it's a very easy question. First you have to check the diode is off or on. If it is on, then I will replace it by a 0.7 volt. Then I will calculate the current in I2. Okay. See the next question. The resistor R1, right, in the circuit below has been adjusted, right, so that my current I1 is 1 milliampere. This current is 1 milliampere, right? And the bipolar transistor Q1 and Q2 are perfectly matched, okay, and have very high current gain, okay. So current gain beta, okay, is equal to IC by IB is very high, right? But the meaning of that means I can ignore IB, can be ignored. This implies my emitter current is nothing but my collector current plus base current will be approximately equal to the collector current, right? Because beta is very high, IB is very small, okay. This is the meaning of having a very high current gain, okay. So their base currents are negligible, right, which already we have explained. Then the supply voltage VCC is having 6 volt, let us take 6 volt, okay. The VT thermal voltage is 26 millivolt, right? Then what is the value of R2 that will make my current I2, okay, a 100 microampere. Okay. So this is a very nice question. Okay. So since the emitter current is I1 and I am ignoring my base current, so the collector current also will be I1, and the same current will flow through my R1, because the current through R1 will be I1 plus 2 times the base current, right? This is one base current, this is another base current, this is IB1, IB2. Okay. IB1, this is IB2. Okay. So IR1 equal to current in collector is I1 plus IB1 plus IB2. But since the base currents are very small, so I can approximate I1 is equal to I1 only. Right? This is the first condition. Okay. So let us try to solve the question to get R2. Right. So if I apply, right, a KVL, right, this is my VB1, this is my VB2, right? So if you take a KVL like this, right? So what is the KVL? VB1, right, minus VB2, right, minus I2 into R2, because the collector current I2 flowing into my emitter because base current is very small, equal to 0. Okay. This implies I2 into R2 equal to VB1 minus VB2, right? This implies R2 is equal to VB1 minus VB2 by I2. So this we have to solve. Okay, equation 1, let us take it. What is VB1? VB1, for VB1 the current flowing is I1. Okay, I1 equal to I0 into exponential of VB1 by VT. Okay, and neglecting the minus 1. Okay, so what it will be VB1? VB1 will be, right, take ln both sides, ln I1 by I0. Question 2. Similarly, what is I2? I2 will be equal to, since both Q1 and Q2 are matched, so the I0 will be remaining same. Okay, into, so I0 is nothing but a reverse saturation current. Since both are exactly matched, so it will be same, right? VB2 by VT. This implies what will be VB2? VB2 equal to VT ln I2 by I0, equation 3. Okay, put equation 2 and 3 in equation 1. This implies R2 is equal to VB1 minus VB2 by I2 equal to, VB1 is VT ln I1 by I0 minus VT ln I2 by I0 divided by I2. Okay, equal to VT ln A minus ln B is equal to ln A by B. So ln A by B, I0 will get cancelled. I will get ln I1 by ln I2 divided by I2. Okay, so let us put the values. So I will go to, this is VT is nothing but given 26 millivolt, right? 26 millivolt into ln I1 is given 1 milliampere, I2 is given 100 microampere, right? So 1 milli by 100 micro divided by 100 micro. Okay, let's calculate this one. So 26 into 10 power of minus 3, right? 26 millivolt into ln 1 milli minus 3 divided by 10 power of minus 3 divided by 100 micro. 100 into 10 power of minus 6. Okay, divided by 100 micro. 100 into 10 power of minus 6. So I got 5 9 8 98.6 ohm. Okay, so the answer should be 598.6 ohm. Okay, so see, we have to put in this equation. Okay, then we will get the answer. Okay, let's see the next. So it's a very easy question, right? Just you put a KVL in this loop, and then you will get the equation as VB1 minus VB2 by I2 is the R2. Then the way to calculate VB1 is very straightforward. If you know the diode equation, it is easy to calculate VB1. Similarly, VB2. Just plug in all these values in R2 to get the answer of R2. Okay. Let us see the next question. Which one of the following statement is correct about the AC coupled common emitter amplifier operating in midband gain? Okay. So it is asking about coupling capacitor and bypass capacitor, right? So if you see, if you take a common emitter amplifier, right? Common emitter amplifier, there are some there is some coupling capacitor at the input to couple the input. Okay, see, there is a coupling capacitor at the output to take the output V0. There is some coupling capacitor at the emitter C. This is CB. This is CC. Okay, these are the external capacitor, right? This is for coupling the input. This is for taking the output. This is for DC biasing, right? I don't want my gain to reduce for my signal, so this is providing a short path to my signal, but it is fixing my DC bias. Okay, so let us not discuss about the functionality of the capacitor. Okay, so thing is, the capacitors are I put externally, right? And the capacitors are in orders of tens of microfarad. So this is some order of 10 of microfarad. Okay, microfarad. Okay. So in the, if you see my gain rate, gain versus frequency, you will see there is roll up at the lower frequency. Then in midband it is almost remaining constant. Then at a higher frequency again it will start rolling off. Okay. So this behavior corresponds to the external capacitor CB, CC and CE. Okay. In midband gain rate, what happens? In the midband, what happens? 1 by frequency is small, right? Frequency is F mid into big capacitor, right? So in this midband rate, just after a frequency called FC cutoff frequency, the frequency is high and C is also high. So 1 by 2 high become very, very low. Okay. So the impedance offered by these capacitance CB, CC and CE in the midband, okay, is very, very low, can be treated as a short circuit, because 1 by frequency in the midband by a high capacitor, right? 1 by high and high will be low only. Okay, so these capacitors are behave as open circuit in the midband, right? Then there are something called parasitic capacitance, right? You know, between base to emitter, there is a capacitor called junction capacitor, right? You can say the CT called transition capacitance plus depletion capacitance, right? So there are two types of capacitance in the we know in a PN junction diode there are two types of capacitor. One is called CT transition capacitor, another is called CD depletion capacitor. The depletion capacitor, because of the depletion region in the PN junction, okay, so this the transition capacitance or I can say it's called C diffusion, right? Diffusion capacitance. This will come into picture when I forward bias the diode. Okay, whatever may be the reason, right? There is a capacitor which is built into the device, right? Which is not external, right? I just briefed you The capacitance mainly because of the depletion region of the PN junction, and whenever a junction is forward biased, there are a charge carrier injection. So because of the more charges in the base and emitter, there is a capacitance called transition capacitance. Okay, so between base to emitter, there are two kind of capacitor. One is CT, one is CD. Similarly, base to capacitor also I have CD, generally CD. So this is CD plus CT. Okay, so these capacitors are built into the device from the device operation, right? And these are very these CD, CT are very high, very small, very small. Okay, so 1 by the impedance is nothing but 1 by C into F proportional to 1 by C into F, right? Here also the impedance proportional to 1 by F into C. So since C is very small, right, in the frequency up to midband, right, this will behave like a very small into the frequency up to midband, right? This will behave like a very small quantity. So 1 by small is very large. Okay, so in the midband, right, the parasitic capacitance behave like a open circuit, because 1 by the capacitor is very small, and if I don't cross the midband, right, the impedance afforded by the capacitors, which is nothing but CD, CT, and nothing but base to collector junction capacitance and base to emitter capacitance. Okay, these parasitic, or I can say intrinsic capacitors, afford very huge impedance when the frequency is below the midband frequency. Okay, so they are very they are offering very large impedance. So this can be treated as a open circuit. Okay, so the parasitic capacitance behaves like a open circuit, and the coupled capacitor behaves like a short circuit. So I think the option A is correct. Okay, why? Because since the parasitic capacitance value is very small, so it behave like a open circuit. Since my coupling capacitors or bypass capacitors, since the value of coupling and bypass capacitor is very large, so they behave like a short circuit in the midband. Okay, let us go to the next question. The transistor geometries in a CMOS inverter has been adjusted to meet the requirement of worst case charge and discharge times of the driving a capacitor C. Okay, the design is to be converted to a NOR gate like shown in the figure. Okay, in the same topology, so that its worst case charge and discharge time while driving the same capacitor should be similar or are similar. Okay, the channel length of all the transistors to be kept unchanged, then we have to find out what should be the width of PMOS and NMOS in comparison to my inverter, right? Okay, so let us answer the question. So for answering this question, right, we have to understand how a charge and discharge takes place of the output capacitor, right? So if you take this, right, take the equivalent model, right, it will be like a switch. Okay, the switch is controlled by my input. Similarly, below also is a switch controlled by my input. This is ground, this is VDD. There is a capacitance here. Okay, see out. Okay, so you see, when my capacitor C will charge to VDD, whenever this switch will be closed, let the resistance offered by my PMOS be RP, let the resistance offered by my NMOS be RN when it is closed. Okay, so when my output will go to VDD, when my input will be, when an input will be low, right? When input will be low, or the switch will be closed, the switch will be open. So the comparator will charge like this to VDD. Okay, so it will charge through a resistance RP and comparator C. So the charging time, right, tau proportional to, so when my V out, okay, going from 0 to VDD, right, the tau I can say tau going from 0 to VDD means tau 1, okay, equal to, so when this will close, right, it will charge. So my tau 1 will be, or I can say tau 0 to 1, I can say it is proportional to my RC time constant, right, RP into C, right. Similarly, when my V out will go from VDD to 0, right, what will happen? My input will be high, or it will be closed, it will open, it is open. So then my output will go from VDD to high. So my tau from 1 to 0 will be proportional to Rn into C, right? So Rn is the impedance offered by my NMOS. Okay, so I understand my charging time constant and my discharging time constant, how it depend on. Okay, so I want the same time for my NOR gate also. Okay, so let us build a similar circuit to my NOR gate. I have a VDD, then we have a input, then I have another transistor, we have another input, a switch, okay, then we have my output V out, okay, then there are two transistors in the bottom, okay, this is my ground, okay, so this is connected to in 1 and this is supposed connected to in 1, this is connected to in 2, connected to in 2, okay. So this is the case of, understand the case of inverter. In case of this one, right, in this one, suppose my output will want to go from VDD 0 to VDD. When it will go, when both in1 and in2 will close, right, when both this PMOS will be on, then only I will get a path to charge from 0 to VDD. So when both will be on, so this is suppose RP, this is again RP, this is RN, this is RN, right. So if both want to charge, right, this is the worst case, right. So my output V out go from 0 to VDD, right, this path, this is the only path, right, will go from 0 to VDD. So you see it is charging through resistance RP and RP, 2 RP. So here tau 0 to 1 proportional to 2 RP into C. There is a comparator of the output. So I can put it in this set. C. Okay. So you see the worst case charging time, right, 0 to VDD, right, is increased by 2 times because it is charging through 2 RP. Okay. So in order to make my charging time, in case 1 is RP into C, in case 2 it is 2 RP into C, we have to make this PMOSes, right, 2 times bigger, right. So double by W of PMOS in NOR gate should be 2 times the W of PMOS in inverter. Okay, if I make 2 times, right, the resistance offered by this will be half. So my tau, the charging time constant will be 2 into RP by 2 into C. So if I make this, then the RP will be RP by 2. This also will be RP by 2. So if I make my W of PMOS in NOR gate 2 times the W of inverter, then the resistance will be divided by 2 and 2. So I will get 2 into RP by 2 will be equal to 2. So I will get new case. So let us right here 2 into RP by 2 to see. This is the case if I take a double by L of this one, right? This is originally if I take same as inverter, but I have to take double the size to make my resistance path same as inverter. Okay, so the size of PMOS in a NOR gate should be more than 2 times the inverter. Okay, now come to the bottom case. So now when my output, right, we out want to go from VDD to 0, right? So here the output can go either of the one will be on, right? Suppose this will be on, it will go through like this. Output will go from VDD to 0. Even if this will be on, again the output will go from VDD to 0, or both will be on, it will go through VDD to 0, right? So what is the worst case? The worst case will be only one will be on, right? If both will be on, it will be Rn by 2, right? Resistance Rn parallel to Rn. If both will be on, the resistance will be Rn parallel to Rn, it will be Rn by 2. It is not the worst case. The worst case is only one will be on. So one will be on means what is the time constant? Tau 1 to 0 proportional to Rn into C. So it is same as the inverter. So the worst case time going from 1 to 0 proportional to Rn into C in both the case, right? In inverter and also in NOR gate. So the NMOS should be the W of NMOS in NOR gate should be equal to double of NMOS in inverter. Clear? So the answer should be, you understand that width of PMOS should be doubled while the width of NMOS should be halved. No, this is wrong. Width of PMOS should be doubled. Width of NMOS transistor should not be changed. This is the answer, right? Because in order to make my charging and discharging time similar, I have to make PMOS doubler and NMOS should be same as inverter. Okay, I think this is clear to all of you. Proceed next. This is a 2-mark question. Okay, but easy question. The switch AC in the circuit shown has been closed for a long time, right? And it is opened at t is equal to 0, right? And remain opens after that. Then assume that a diode has a reverse current and 0 forward current drop. So assume that diode has a 0 reverse current, means it is open in reverse bias, and 0 forward voltage means it is closed, it will be short in forward bias. So it's like an ideal diode. It means it's an ideal diode. Okay. In reverse bias, current is 0. In forward bias, voltage drop is 0. It's an ideal diode. Okay. In this condition, what is the steady state magnitude of voltage comparator VC? Okay. First condition is t less than 0. Right. For t less than 0, for longer period of time, right, the switch is open, switch is closed, right? Switch is closed, given that switch is closed for a long time before t is equal to less than 0. So since switch is closed, right, the current will flow through like this, right? Since for long time the switch is closed, the inductor will be like a short circuit, okay? And since inductor is short circuit, the diode is open, right? For long time switch is closed. This implies this will be like a short, this is grounded, so my diode also is open. Okay, what is the equivalent circuit? Inductor will be like a short circuit for long time charging, right? Then diode is open and there is a capacitor VC. Okay, then micro. So this is the condition of my circuit for t less than 0, because the inductor will be like a short circuit for a longer time it is charging. Okay, 1 ohm. But the current through this current will be 10 by 1 ohm, is the current IL will be equal to 10 by 1 equal to 10 ampere, right? Now when the, so this is my positive, this is my negative, right? Negative. When at t is equal to 0, right, it is open, right? The current 10 ampere in my diode should not reverse, right? If it reverse, there is infinite voltage that will flow through the, that will generate into the inductor, right? This 10 ampere, if I open the switch, should flow through like this only, right? So for making my inductor current flowing in the same direction that is flowing through before the switch is closed, switch is open, right? Again, let me repeat. At t less than 0, 10 ampere current is flowing through the inductor. When at t is equal to 0, we open the switch, right? The same current should flow through the inductor, because the inductor current cannot change instantaneously. If it changes instantaneously, the voltage drop in that inductor is LDI by dt will be infinity. So which is not possible. So for making the current to flow in the same direction, what will happen? The inductor voltage will change. How it will change? For t greater than equal to 0, what will happen? Since the switch is open, this is not in the picture, right? What will happen to my inductor voltage? Inductor voltage will be changing like this to make a 10 ampere current flowing through the inductor in the same direction, right? Then since the voltage is reverse, and diode will be short because it will be reverse bias, it will be forward bias, and my capacitor will charge. See, like this. Okay, so this 10 ampere is the initial current at t is equal to 0. To flow the same current in the same direction, my inductor voltage have to change from its earlier position, right? It is reversed. When it is reversed, it is forward biased by diode D. Then the current will flow like this, and the capacitor will start charging. Okay, so in order to find the voltage in capacitor, we have to go to the Laplace transform, right? So let us convert the circuit into Laplace transform. Okay, so if I want to convert into Laplace transform, right? What is the condition now? See, the condition is there is a initial current of 10 ampere. Okay, 10 ampere I can say this is a capacitor, right? Minus plus. Okay, this 10 ampere is IL 0 plus equal to 10 ampere, right? You see, this is suppose L. Okay, now you have to go to Laplace transform, right? Taking the initial current in the inductor as 10 ampere. So you take the initial current in the inductor as 10 ampere, then convert it into Laplace, right? If you convert into Laplace, right, it will be Ls. Okay, and there is a current that is flowing through, change to 10 by S. Okay, current is 10 by S. Okay, the capacitor impedance is given by 1 by SC, right? Now, if you impedance Ls is in parallel with a current source, I can convert it into a. So when the impedance, when the current flow through my Ls, what is the voltage? Voltage will be Ls into 10 by S minus and plus like this, right? So Ls into 10 by S will be L into 10, right? Because when the current will flow through my Ls, right? So I want to replace this by a equivalent voltage source in series with impedance, right? Now I replace, first step I replace it with a equivalent impedance with in series in parallel to a current source. Now the same can be converted into a voltage source in series with impedance, right? What is the voltage of the voltage source? Nothing but 10 by S into Ls, nothing but L into 10. Since it is going like this, so it will be plus, this will be negative. So this is negative, this is negative, this is positive. So I have a Ls, right? Then the impedance is given by 1 by SC. Okay. So now this is the equivalent circuit in Laplace domain. Okay. So let me repeat again. Since there is a initial current of flowing 10 ampere, there is a current source of 10 by S that is flowing through, and the impedance given by this inductor is Ls, we know, and then I can convert this impedance Ls parallel to the current source in equivalent voltage source in series with the impedance, right? Is it clear? Now, what is the voltage across the comparator? Nothing but VCS, right? VCS equal to this voltage source will be like a voltage divider, right? Voltage divider. So it will be L into 10 into 1 by SC divided by 1 by SC plus LS, right? Because this is like a voltage source divided between the LS and 1 by SC impedance, right? This is impedance is having the impedance is 1 by SC. Here the impedance is LS. So the voltage source will be like a voltage divider. So the voltage across capacitor C is nothing but V into 1 by SC divided by 1 by SC plus LS. It's like simple resistor divider kind of thing. Okay. So equal to, I will take the SC below. So I got L into 10, right? L into 10 divided by 1 plus S SCL. So is SC if take to downside, right? SC get cancel. SC into SL will be S square into LC, right? This is my VCS. Okay. So what I got VCS is equal to 10 into L, right? 10 into L divided by S square LC plus 1. We'll take LC common. So I got 10 by C S square plus 1 by LC. Okay. So if I do some changes now, I know the if I want to make it into square, right, it will be like L0 square, right or not? I know because in order to take the inverse Laplace transform, I have to express in terms of S square plus A square, right? So here I have done the like this. So what will now VCS is nothing but 10 by C, just multiply 1 by root LC, divide 1 by root LC, right, into S square plus 1 by root LC the whole square. Okay. Now you see 10 by C and root over LC. If I multiply, what I will get 10 into root over of L by C, right or not? C will go this side, will cancel into 1 by root LC, right, by S square plus 1 by root L0 square. Okay. So let us take this as a constant equal to, suppose let us take it as a P, let us take it as a B, let us take it as A. So I got B into A by S square plus A square, right? So what is the inverse Laplace transform of A by S square plus A square? We know. So B of T will be the inverse Laplace transform of this one, right? ILT, inverse Laplace transform will be B into sin AT, because sin AT Laplace transform is A by S square plus A square, right? So here B is nothing but 10 into root over of L by C into sin A is nothing but 1 by root over LC into T. So this is my voltage of the capacitor at time t is equal to greater than 0. So let us put all these things equal to, from which I got 10 into root over of L by C into sin T by root over LC, right? T by root over LC. This is my answer. Let's put all the values. What is L? L is 1 milli. What is C? C is 10 micro into sin of T by root over of 10 micro into 1 milli, right? Let's put all the things. I got 10 into root over of 1 milli minus 3 divided by 10 into 10 power of minus 6. Okay, how much it is getting? You got 100 into what is root over 1 by LC? 1 by root over of L into C. L is 1 milli into C is 10 power of minus 5. So I got just a minute. So I got sin 10 power of 4t is my Vc of t for t greater than 0. For t greater than 0. Wait, this is the answer. So let me brief you what we have done. First thing is what we have done is we calculated the current through inductor for t less than 0, it is 10 ampere. The same current have to flow for t greater than 0. Okay, at the same instant. Since my inductor current cannot change instantaneously, so my inductor voltage have to reverse for flowing the current in the same direction. So since my inductor voltage is reversed, it is making my diode forward bias and my capacitor will start charging like this. Then we converted this circuit into a Laplace transform because taking the inductor current at 0 plus H 10 microampere. Then we know the Laplace transform of L with initial current of 10 ampere is SL into SL parallel with a current source of 10 by S. Then we converted this current source in parallel with the impedance to a voltage source in series with impedance. Okay. Then the calculation is very straightforward. Simply a voltage divider. Then we have done some calculation. Then calculate the Vc of S. Then we have done the inverse Laplace transform to get the Vct. Right? Now Vct will be 100 into sin 10 power of t. Okay. This is the answer. Let us see the next question. Consider a long channel NMOS transistor with source body connected together. Assume that the mobility of electron is independent of VGS and VDS, given that GM of is this for VDS is equal to 50 millivolt and VGS is equal to 2 volt and GD is equal to 8 microampere plus volt for VGS is equal to 2 volt and VDS is equal to 0 volt. Right? Then where it is defined that the transconductance GM is equal to dID by dVGS and the output conductance GD is nothing but dID by dVDS. Okay. So with this information, right, we need to find out the VTH or the threshold voltage of the transistor. Okay. So let us try to solve this. So you can see, right, the VDS, we know for this first case, right, GM is nothing but dID by dVGS. Right? Here, first thing is, since VDS is equal to 50 volt and VGS is equal to 2 volt. Okay. So we assume that VDS is less than VGS minus VTH. Even though I don't know VTH, since it is 50 millivolt, very less. So we can assume that the transistor can be operating in linear region because VDS is very small, 50 millivolt only. Okay. So I can assume that my transistor is in linear region. Okay. So when my transistor is in linear region, right, I know the diode, the current in the drain. Okay. Since my MOSFET is in linear region equal to mu1 COX double by L into VGS minus VT into VDS minus VDS square by 2. Okay. And since VDS is very small, 50 millivolt, I can ignore this term. Okay. So ID will be equal to mu1 COX double by L VGS minus VTH into VDS. Okay. Now what is GM? GM is equal to simplest GM is equal to DID by dVGS. So we have to derivative this with respect to VGS, right? It will be equal to mu n COX double by L. So if you derivative this is, we will get 1 into VDS. Okay, this is my equation 1. Okay, this is my GM already given in the question. The second thing is, it is given GD, given DID by dVGS dVDS. Okay, and when VDS equal 0 volt, right? When VDS equal 0 volt, definitely we are in linear region, right? So I can put the equation again same as previous, mu n COX double by L VGS minus VTH into VDS. Okay, so what is DID by dV? So what is GD? GD equal to DID by dVDS equal to mu n COX double by L into VGS minus VTH. Okay, this is equation 2. Okay, now let's take the division of equation 1 and by equation 2. Let's do equation 1 by equation 2. This is nothing but GM by GD. Okay, what is GM? GM is given this one, right? Mu n COX double by L into VDS. Okay, GM is nothing but mu n COX double by L into VDS divided by GD is mu n COX double by L into VGS minus VTH, right? VGS minus VTH. Now put all the things in place. What is GM? GM is given 0.5 microampere per volt divided by GD is 8 microampere per volt is equal to this get cancelled. VDS is given 50 millivolt. VGS is given 2 volt minus VTH, right? This implies 1 by 16, right? 1 by 16 equal to 50 millivolt divided by 2 minus VTH. Okay, this implies 2 minus VTH equal to 16 into 50 millivolt equal to how much? 16 millivolt is how much? 16 into 50 millivolt. 0.8. 0.8. This implies VTH is equal to 2 minus 0.8 is equal to 1.2 volt. Okay, so answer is 1.2 volt. So it's a very easy question, right? Only thing in this is you have to understand that transistor is operating in linear region. So you have to put this equation while calculating GM and GD, right? Then everything is straightforward. Okay, let's see the next question. So in this question, right, the figure shows a half wave rectifier, right, with a 475 microfarad filter capacitor, right? The load draws a constant current of 1 ampere, right, from the rectifier. Okay, the figure shows an input voltage Vi like this, the output voltage Vc, and peak to peak voltage ripple of Vc, right? Then when the input voltage is a triangle wave with an amplitude of 10 volt, right, period of 1 millisecond, then we have to find out the peak to peak ripple of my capacitor. So this question looks little complicated, but it's a dead easy question. Okay, how? You see, initially, right, my capacitor will, because initially when during my positive excursion, whenever my Vin will be greater than 0, right, my capacitor will start charging to my Vin, right? Then will start charging to my Vin. Okay, so I'm taking it have charged to Vin longer time before. So initially during positive half cycle, it will start charging to Vin. Then when my Vin is decreasing, right, already my VC is almost V in, then my V in is decreasing, then this will be reverse bias. This will reverse bias means my comparator will start discharging because my output current is constant 1 ampere. So this 1 ampere current will be provided by the capacitor. Right? Whenever the diode is forward biased, the input will provide current to capacitor, also to the load. Right? So let me summarize here. When diode forward bias, V in, okay, will charge the capacitor and provide load current 1 ampere. Right? When diode is reverse bias, right? When diode reverse bias, the 1 ampere current is provided by capacitor. Okay. So it is charged to V in. When V in is reduced, right, then diode is off. Then during the entire period, the capacitor will discharge because it is providing the current 1 ampere. It will go on discharging, right? Again, when my V input will increase, will be little more than my capacitor voltage. Again, my capacitor will charge to my input, right? Again, after that, again my capacitor will discharge because diode will be reverse bias and it will go on discharging until my input again more than my capacitor voltage. When it become more than my capacitor voltage, again my capacitor will charge, right? So this is the charge discharging cycle of my capacitor. So when diode is forward bias, my capacitor will charge and it will provide my when diode is forward bias, my V in will provide charge to capacitor, also it will provide current to the output load. Okay, then during the diode it is off, the capacitor will discharge whatever charge it was there previously. When diode is on, when diode is off, the capacitor will discharge. Okay, so you see, when V in is reduced, right, reduced, the capacitor is discharging because it is providing current to the load. It will go on discharging. Again, when my input is crosses my BC at this point, again my capacitor will charge in the short interval to my input. Again, my input when it is reducing, my capacitor will go give the whole current to the load. Okay, this is the phenomena happening. Okay, so you can see almost for the one period, right? You can neglect this time period. Okay, almost for the one period of t is equal to 1 millisecond, my capacitor is giving current to the load. Okay, I know my current to the capacitor is nothing but C dV by dt. So if my capacitor is giving current 1 ampere for 1 millisecond, what is the voltage drop in the capacitor? That's what it is asked in the question. Okay, since my capacitor is providing 1 ampere current for almost 1 millisecond approximately. So what is the change in voltage of the capacitor when it discharges for 1 millisecond giving 1 ampere current? Okay, so this implies dV is equal to IC into dt divided by C. What is IC? IC is during discharging it is 1 ampere into time is 1 millisecond divided by what is the capacitor? Capacitor is 475 microfarad. Right? This much is the change in capacitor voltage when it is discharging because the load is taking current from the capacitor for 1 millisecond. Okay, so let us calculate the change in voltage. 1 into 10 power of minus 3 divided by 475 into 10 power of minus 6. So I got change in voltage is 2.105 volt. Okay, so this much voltage will be changed in my capacitor peak to peak when it is discharging by giving 1 ampere current to the load for 1 millisecond. This is a very easy question. Okay, the next question. So this is a very Nice question. Okay. In the op-amp circuit shown in the figure, right, the general diode Z1, Z2 clamp the output voltage to +5 or -5. Right. If my output is plus VCC plus V saturation plus 10, it clamp the output to -5 +5. If my output is -10, it clamp the output to -5. Okay. So because you see there is a positive feedback, right? Positive feedback. So it behaves like a comparator. Okay. So my output here can be +10 or -10. So when it is +10, what is my output here? It will be +5. When it is -10, my output here will be -5. Okay. So the output V0 can be only two value, +5 or -5, because it is a comparator. It's behave like a comparator. So the output can be here only +5 or -5. Okay. The switch SC is initially closed and is opened at time t is equal to 0. Right. So for t less than 0, right, switch is closed. Closed means what is V negative? V negative is equal to minus plus 10 volt. 10 volt. Right or not? Since V negative is 10 volt, right? V negative is equal to 10 volt is definitely greater than V positive, because V positive can maximum be how much? If it is -5, it will be -5 into some division. It cannot be 10 volt, -10 volt, right? So definitely V negative is greater than V positive. So my V output is -5 volt, because in a comparator, whenever V negative is greater than V positive, my output is plus minus V set. In this case -10. When it output is -10, V0 will be -5. Okay. So for t less than 0, V negative is equal to 10 volt, because 10 volt is directly coming to this V negative, 10 volt. So V negative is greater than V positive. That's why my output V0 is -5 volt. This is the end of the story for t less than 0. Okay. So for t greater than 0, what is happening? Switch is opened. Switch is opened. Okay. It's open. Now, what it is asking? Find the time t1 when my output V0 will changes the state. Okay. For t less than 0, what is my V0? Is -5 volt. Right. When it is -5 volt, right, at t is equal to 0, switch is open. Right. Now the comparator will come into picture. Okay. Then we have to find out at what time my output will switch from -5 to +5. Okay. We have to find out the time. For this thing, first thing is, when my V0 is -5, right? What is V positive? V positive is equal to -5 into 1 kilo, which -5 is here, into 1 kilo divided by 1k plus 54k is equal to 5k is equal to -1 volt. Okay. So V positive is equal to -1 volt when my V0 is equal to -5 volt. Right. So in order to change the output for V0 to go from -5 to +5, then my V negative, right, have to be less than V positive. V positive. This implies V negative have to be less than -1 volt. Okay. So when this point will be less than or -1 volt, like -1.1, -1.2, something like that. Okay. Then my V negative will be less than -1 volt. At that point of time, my output will switch from -5 to +5. Okay. Now the aim is to find at what time my V negative will go to -1 volt. Okay. That is our aim in this question. That's all. Okay. Let us see. For t greater than 0, if I want to replace this circuit, okay, this is V negative, right? V negative. Okay. I want to find out at what point of time and V negative will be less than -1 volt, right? That is my aim. So let us take the equivalent circuit of this for t greater than 0. So this we have is 10 volt. Okay. Then I am just drawing this one. Okay, 10 volt. Then I have a capacitor. Then I have a resistor R is C. Okay, then I have minus 10 volt. Right. So if I want to draw circuit in another way, right, I have minus 10 volt. Right. Then there is a R. There is a R. Then there is a capacitor C. Right. Then I have from here to ground plus 10 volt. Right. R is C. Right or not? So if you see what is the voltage across the capacitor? VCT. VCT will be equal to V infinity into 1 minus e to the power of minus T by RC. We know this is the charging of my capacitor. What is V infinity? During infinite time, the capacitor will be open. What is the V infinity? V infinity will be, suppose this will take positive, right? If you go like this, VC will be 20 because when it is open, right? The voltage here is minus 10, again minus 10 will be minus 10. Okay, what I am telling. Okay, what is V infinity? V infinity is nothing but at infinite time positive, negative. Okay, so this capacitor will be open at infinite time, right? So what is the voltage of the capacitor? VC. Let's take a loop 10. This is 10. So plus to minus to plus, minus to plus means increasing, right? VC. Then plus to minus will be minus 10. Okay, minus 10 VC. VC is nothing but is not V infinity. Okay? V infinity. Okay, this is V infinity is nothing but voltage across the capacitor at infinite time minus 10 again minus 10 equal to 0, right? So if you take a capacitor charge like this, okay, it will be plus to minus minus V infinity, right? Minus 10 equal to 0. So equal to V infinity is equal to minus 20. Right or not? You see, at infinite time, this will be open. If I take this end as positive, this end as negative, what is the voltage across this capacitor? Will be from here to here, plus to minus, right? Minus infinity, again plus to minus, minus 10, again plus to minus, minus 10. So V infinity is equal to minus 20 volt. Okay, so what is VCT? VCT is equal to minus 20 is the minus infinite time into 1 minus minus T by RC, right? This is the voltage in the capacitor. Okay, now what is V negative? V negative is how much? V negative is, we know what is positive. See, I have taken this end is positive, this end negative. Okay, the end connected to resistor is positive, it is negative. I have taken like this. Okay, that's why VCT is coming like this. Okay, so if take this positive, this is negative. The end connected to the 10 kilo ohm resistor, the end connected to the 10 kilo ohm resistor, right? I have taken positive. See, this 10K or R. Okay, this I have taken positive. So here it is positive, it is negative. Okay, so this is my VCT. V negative. Okay, V negative. So let us find V negative. V negative will equal to V negative minus VCT minus 10 equal to 0. This implies V negative is equal to VCT plus 10, right? You see, because I have taken this end as positive, so V negative minus VCT minus 10 is equal to 0. What is VCT? VCT is equal to minus 20 into 1 minus T by RC plus 10. So this is equal to minus 20 plus 10 will be equal to minus 10 plus 20 into e to power of minus T by RC. Okay. Now I have to find out the time at which V negative will be minus 1 volt. So this is equal to V negative will be minus 1 volt. Okay. This implies 9 is equal to 20 e to power of minus T by RC. This implies e to power of T by RC is equal to T by RC is equal to 20 by 9. T is equal to RC ln 20 by 9. Okay, this is the answer. So what is RC? R is given 10K into C is 100 micro into ln 20 by 9. So calculate the time. Time is nothing but 10K into 100 into the power of minus 6 into ln 20 by 9. 0.798 second. Okay. So at that time t is equal to 0.798 second, and V negative will cross minus 1 volt. So my output will change from minus 5 to plus 5. Okay. This is the answer. 0.798. So let me brief you what we have done. The aim is to find the time at which a V negative will be less than minus 1 volt. Okay, that is the main aim. So for doing that, we have drawn the equivalent circuit here. Then this is coming like this. This is nothing but a simply charging up my capacitor. VCT is equal to V infinity into 1 minus T by RC. This is the charging of my capacitor. What is V infinity? V infinity we have taken at infinite time. The VC will be open, right? So it will be open. What is the voltage across the capacitor? It will be equal to minus 20. Then we put in minus 20. We got VCT as minus 20 into 1 minus T power minus 20 into 1 minus e to power of minus T by RC. Okay. Now we calculated what is V negative. V negative is minus VC minus 10. Right? So we got V negative is equal to VC plus 10. Then we got the value of V negative. Then we have find the time t at which V negative will be minus 1 volt. The time is 0.798 second. Okay, this is the answer. So let us see the next question. An op-amp has an finite open loop voltage gain 100, right? A is equal to 100, and its input offset voltage is 5 millivolt. 5 millivolt. Model as shown in the figure. The amplifier is an ideal in all other aspects. Okay. When my V input is 25 millivolt, you have to calculate the V output. Okay. This is a very nice question. Let's calculate V0. You know when gain is finite, what is V0? V0 is nothing but gain into voltage at the positive terminal minus voltage at the negative terminal. Right? This is the condition when my gain is finite. Okay. Equal to A into V positive. What is V negative? V negative is V0 into 1K by minus V negative is V0 into 1K by 1K plus 15K is equal to 16K. Right? So simply V0 into 1 plus A by 16, A by 16 is equal to A into V positive. Right? This implies V0 is equal to 16 by 16 plus A into V positive. V positive is nothing but here VIOS plus V input. Okay, VIOS plus V input. Okay, I'll plug in the value 16 by 16 plus 100 is the gain into VIOS is 5 millivolt plus 25 millivolt. So let's calculate the answer. 16 divided by 1166 into 30 millivolt. 30 into 10 power of minus 3. Okay. Into A. A is there na here. See this A is there. So here you have to do A here because A should be there. Okay. A is 100. Okay. Because A and B positive, then this 16 by 16 plus A have come here. This A should be there here. Okay. So into 100 we have to do. We got 0.413, 0.4137. Okay. So it is asking in millivolt, right? So equal to 413.7 millivolt is the answer. Very easy question, right? Only thing you have to know, the output when my gain is finite is A into B positive minus B negative. Okay. And B negative is nothing but a simple ratio divider. B0 into 1K by 1K plus 15K. Then the answer is easy. So answer is 413 millivolt. Okay. I think that's all. Thank you guys.